Educational Module. Machine Learning. Learning Unit. Advanced. Ensemble Learning. Ensemble learning makes use of methods that combine/fuse multiple algorithms in order to obtain better prediction accuracy than could be achieved from any of those algorithms alone. Each method is attempting to solve the same problem. The learners utilized in an ensemble are called Bayes classifiers, and they don't have to be ones of the same type. Furthermore, the training samples and as a result the learners must be as diverse as possible if we want to achieve a performance gain, since combining identical learners won't affect performance. There are many general advantages that come with ensemble methods. An ensemble can take weak models, which meet a minimum requirement of outperforming random guessing, and convert them into stronger models. In a case where we have a too big or too small dataset, it's more practical and effective to use multiple classifiers. Researchers confirmed the reduction of bias in learners. Another advantage includes also reduction of overfitting in models. An ensemble could also take a fast convergence, low computation complexity or even low accuracy algorithm, and increase the computation that is performed since many algorithms are executed and stacked together. As a result, the accuracy is obviously increased, and a stronger model is built. The generalization ability of an ensemble is typically stronger compared to that of a standalone algorithm. Evaluating the prediction of an ensemble requires more computation and result in a higher time complexity than evaluating the prediction of a single method. Thus, ensemble learning is best suited in domains where computational complexity is relatively unimportant or where the highest possible classification accuracy is desired. In practice, the difference in cost and time is small, because if we were to use a single classifier, we would have to execute it multiple times while optimizing the parameters. Also, while ensembles have been proven to achieve better performance in literature, there are cases where they will perform worse than one of the Bayes classifiers. In ensemble learning, it is vital to achieve diversity if we want a performance gain from the fusion. One of the obstacles is the fact that all learners are trained on the exact same data set, which was built for a single task and usually on a single domain. Additionally, the Bayes learners must also be somewhat accurate. The success of ensemble learning lies in achieving a good trade-off between individual performance and diversity, while understanding diversity is overall crucial. In the case of regression problems, a fitting measure of diversity is the variance of the outputs of learners. The reason being that regression problems are solved by averaging, and is proved that the error of averaging models is reduced by increasing diversity. The main ensemble methods are the following: bagging, boosting, voting, stacking and meta-classification, out-of-the-box ensemble, Bayesian model averaging, and random subspace. In the figure, we can see the general ensemble pipeline / bagging refers to bootstrap aggregating, which uses a sampling technique followed by combining a multitude of Bayes classifiers. In particular, every Bayes classifier is trained on a randomly drawn, with replacement, subset of the training data. As a result, All classifiers will have different training samples and they will be trained fairly different. Bagging is the simplest ensemble to implement. In the FIG, we see the main workflow of the bagging ensemble method. It tends to reduce problems related to overfitting to a higher degree than other techniques, because it is a variance reduction method. It performs well with limited data, as long as there is high cross-classifier diversity in decisions. It improves performance of unstable base classifiers like decision trees. Summarizing, there are 3 steps in bagging. N is the number of base classifiers. Step 1. Generate a bootstrap training sample from the dataset n times. Step 2. Train each one of the n base classifiers on one of the training samples. Step 3. Build an ensemble based on the n base classifiers, using a method such as majority vote. Boosting executes the base classifiers in a sequential, iterative, order, thus creating the ensemble incrementally, with each new classifier attempting to predict previously misclassified data. Boosting attempts to convert weak models, which meet a minimum requirement of outperforming random guessing, into stronger models. It could be considered a model averaging method. Because of this attempt to focus on misclassified data, boosting focuses on the most difficult instances, which can be both an advantage and a disadvantage. The main workflow of the boosting ensemble method. Boosting uses sampling with / without replacement on the input training data. Every new sample makes the mistakes of the previous learner more evident. However, the samples are assigned weights which change through time, based on the accuracy of the classifiers. At the start, the weights are initialized to 1 from m, where m is the total number of data instances. The basic idea is to force the base classifiers to focus on samples that were misclassified by previous base classifiers by running the classifier on modified versions of the initial dataset. As a result, samples that were not predicted correctly will have a higher weight. A popular practical boosting technique is AdaBoost, named after adaptive boosting. Summarizing, the following 4 steps are executed for n iterations, where n is the number of base classifiers. Step 1. Generate or draw a training sample I from the dataset to train the ith classifier. Step 2. Evaluate the performance of the ith classifier on the entire training set. Step 3. Mark the misclassified cases so that they can be taken into consideration on the next iteration. Step 4. After n iterations, build an ensemble using a method such as majority vote. Voting is a very common and simplistic method that combines learning algorithms in the same way that people vote in real life. Each algorithm makes a decision which consists its vote. The class with the most votes is chosen by the majority vote method. There also exist variations such as weighted majority vote. In stacking, each base classifier is run independently and all the predictions that are retrieved are used as input on a new learning algorithm. The final machine learning classifier / algorithm is called a metaclassifier. In a way, the predictions of the base classifiers are used to generate a new training data set. It is suggested to not use the same data instances to train the base classifiers and to generate the new data for the second-level classifier. Stacking typically achieves better accuracy than standalone base classifiers, and the most commonly used meta-classifier is logistic regression. It can also be used to estimate Bagging's error rate or to select the best classifier by cross-validation. In the following figure, we can see the main workflow of the stacking method.